It's my pleasure to introduce Céline Swennenhuis, who will be speaking today about bin packing. This is a paper that will appear in SODA next year, and it is also a result that was partially discovered during our Céline Sasdui workshop in February this year. So, Céline, please.
Yes, thank you. Just a quick thing, if there are any questions during the talk about if you're not sure, if you understand something, please interrupt me, because I think it's better to explain it at that time than to backtrack a few slides. So just interrupt me if you want to ask anything. So thank you that I can present here. It's really nice to be back in Warsaw. So this is joint work with Jasper Nederlof, who's my PhD supervisor, who's in Utrecht University, Jakob Pavlovic, Karol Wędzinski, and me. And indeed, this was started at the retreat last February with the three of us, and then Jasper joined in because he had a lot of knowledge about the subject. So before I am going to explain what we actually did, I'm going to first introduce bin packing, just to make sure that everyone's on the same page on what we're talking about. So in bin packing, we're given a number of items, and for each item there's a given weight, W of J, and J is then the item, and there are N items. So for example, we have these items here, and there's a given weight for each of them. And I'm also going to denote W of X, where X is a subset of the items, and then I just mean that we just sum the weights of the items in that subset. And we're also given M, which is a number, and we have that number of bins, and each with a capacity C. So in this example, we have 4 bins with a capacity each 8. And then the question is, can we distribute these items over the given bins without exceeding their capacity? And the answer in this case is yes, because we can move these 3 into the first bin, these in the second bin, this in the third bin, this in the fourth bin. And indeed, we can distribute all the items over the 4 bins without exceeding their capacity, so we have a yes instance. So today we're going to assume 2 things, and we need these assumptions to have a presentation that's within 45 minutes. And I will explain something at the end of this presentation how we can get rid of these assumptions, because it's not entirely clear how you can do that. And 2 assumptions are that the instances are tight. With that I mean that all the bins are completely filled. So the sum of all the weights is exactly equal to all the capacity that we have. And the second assumption that we have is that the instances are balanced. And with that, I mean that K bins have exactly half of the items. So for example, if this is the solution, then if I look at the first K bins, then it should have exactly half of the items, and the rest of the items should be in the rest of the bins. That's an assumption that we will use heavily during one of the algorithms. Okay, so what is known about bin packing? There are 2 algorithms that are that work fairly well. So the first algorithm is dynamic programming, and it runs in the capacity to the power number of bins times n. And I'll quickly show and introduce that in a couple of slides. And the second algorithm is an algorithm that is based on Björk-Puntesfeld and Koi-Visto, which did an algorithm on set cover, and you can change it a little bit, and then you have an algorithm for bin packing as well. And that runs in order 2 to the n times n time. And we're going to use some kind of extensions on these 2 algorithms today. So one of the main questions is, can we do this in faster than 2 to the n time, so 1.999 to the n time? And this is a question that's asked more often. For example, there are a lot of hypotheses that some problems cannot be done faster than 2 to the n. People think about that for Hamiltonian cycle. So it's an interesting question to see whether this is true for bin packing as well. And we are not able to answer that question, but we're coming quite close. So our result is the following. We can do something faster, so 2 minus epsilon m to the power n, with epsilon m being something positive. That depends on m. So for each number of constant bins, we can actually do something faster. But this epsilon m is small, so that's just something to notice. Is this entirely new? Well, quite, because before it was only known for 2 bins or 3 bins. 2 bins is a problem where you just have a subset sum. And 3 bins, there was an algorithm by Lente et al. Who had an algorithm called sort and search, which I'm not getting into today, but they were faster for 3 bins. And from 4 bins and more, there was actually not known, and the best algorithm seems to be this alteration of pure Q and Twistfield and pure Histo for the 2 to the n algorithm. Okay, so then we got to work on it. And on the 25th of March, we got to 6 bins. And then a little bit later, we got to 40 bins with some new ideas. And then a little bit more later, we got to 48. We got some new ideas again. We got to 122 bins. And then that's where we thought, okay, probably this is possible for all constant number of bins. And indeed, 1 week later, we found a way to prove this for any constant number of bins. So what's the idea? The idea is really this trade-off between the 2 algorithms that I just told you about. So either algorithm A is going to be a fast algorithm, or at least faster than 2 to the n, or algorithm B is going to be faster than 2 to the n. And that depends on 2 parameters, which I'm going to introduce extensively here, which are alpha of W and B. So alpha of W is the number of weights that we can generate with this weight function. So all the weights that we could possibly have as a subset of the items. And B is the number of subsets that have exactly the same weight. So either we're going to show that either alpha of W is small or this set B is small. And depending on that, algorithm A is going to be fast or algorithm B is going to be fast. So let's dive into the algorithms. So first algorithm, oh, sorry, I forgot. I just want to make sure that everyone's on the same page with alpha and B because I have more time than in my old presentation. So just to make sure that everyone's on the same page on alpha and B, I'm just going to present 3 examples. And I hope everyone exactly knows what they mean, because otherwise they're going to be named in every other slide from here on. So if we have only weights 0, so all my weights are 0, then the only weight that I can generate is just 0, of course. It doesn't matter which subset you take, the total weight is going to be 0. So alpha is going to be 1, and there are 32 sets that have all the same weight. The other extreme case is actually when we have powers of 2. So if I have weights that are 1, 2, 4, 8, 16, then there is, like, we can create weights 0 up to all the way up to 31. So there are 32 different weights that we can generate. However, for each weight, there's only one specific way to get to that specific weight. For example, if I want to have 15, the only way to get to there is to have 8, 4, 2, and 1. 8, 4, 2, yeah, 8, 4, 2, and 1. So there's only one way to get to a specific weight. So indeed, this B is always going to be at most 1. Third, more natural example is going to be when we have a little bit more random numbers. So just say 1, 2, 3, 4, 5. Then there is going to be 16 different weights that we can generate. And at most 3 sets sum to have the same weight. Okay. Since there are no questions at this point, I hope everyone agrees on these 2 definitions. And we're going to algorithm A, as I promised. So algorithm A is just a dynamic program where we have table entries, and they are indexed by J, which is just a number of item, and leftover capacities. And we're going to say that Tj C1 to Cm is true. We can fit items 1 up until item J into bins with leftover capacity C1 to Cm. And we can compute this by just this fairly simple formula. We're just going to try for item J, whether it fits in bin 1, bin 2, bin 3, bin 4, etc., all the way to bin M. And we just subtract that weight, and we're just going to look if the rest of the items then fits in the leftover capacities that we then have. So we just look at this quite stupidly. Actually, we get a C to the M algorithm, where C is the capacity. But we can do something a little bit better if we're doing something smart. So remember, this alpha, we can actually do runtime alpha to the power m times m squared. And this is because we don't need to look at all the different weights. We only need to look at the weights that are actually present in our weight function. So for example, if we have all the weights are 2, so all the items have weight 2, then we actually only look at weights 0, 2, 4, 6, 8, so only the even weights. So it'd be really weird to incorporate an odd number in the capacities. And in this way, we actually get something better in our runtime. So in this case, it actually gives us something better. But again, if we use the powers of 2, alpha of w is actually 2 to the n, because we can make all the weights up until 2 to the n. So in that case, this algorithm will become like really, really, really slow, and we don't want it. But we can conclude that if alpha is smaller than 1.99 to the n over m, then this algorithm runs in time 1.999 till the end. So as long as this alpha is smaller than something of 2 to the n over m, then we can do something faster with this algorithm. So that's something to remember. And now we get into the second algorithm. And to explain this algorithm, I'm going to use this diamond on the right, which is going to be my subset lattice. And with that, I mean that any point in this lattice is going to be a subset of the items. And it's going to be sorted from small item sets to large item sets. So here on the bottom, there's the empty set. And all the way up the top, there's the set of all the items. And just so that we're all on board. So if we look at all the sets of size 1, it's just 1, 2, 3, all the way like just n. And if we look at the sets of size 2, they're here and they're like 1, 2, 1, 3, 2, 4, 3, 6, anything of that kind. So just a quick notion is that like this diamond looks really beautiful here, but if you would really draw it as big as it is, it would be like exponentially large, but we don't have space on this presentation, of course. But just to notice that there's exponentially many sets at this line here of n over 2. Okay, so the theorem that we're using is that for x, a subset of the items, we can compute in time relative to the down closure of x, which is all the subsets of x, whether x can be distributed over n bins. So if we take an x here, and then this is its down closure, so all the sets that are a subset of it, and in time relative to this down closure, we can compute whether x can actually be distributed over n bins. How can we use this? Well, if we then just take x to be all the items, so up in the top here, then the down closure of x is just the whole subset lattice, and the whole subset lattice is of size 2 to the n. So we get our algorithm of 2 to the n times n that I promised earlier. How do we do this? Well, for the people who've seen this before, it's based on inclusion-exclusion formulas and fast algebraic transformations, set Mobius transformations to be specific. And it just comes down to computing this thing here. And if that's bigger than 0, then we're happy. And if it's not, if it's 0, then we know that there's not a solution. And therefore, the statement is actually also a little bit stronger. The theorem is that for B family of subsets, we can compute in time the down closure of B, whether x can be distributed over n bins for all x and b at the same time. So we can take, for example, B to be 3 sets. So maybe these 3 sets. And then we can compute in time relative to the down closure of B, which is the whole blue area here, whether we can distribute x1, whether we can distribute x2 and x3 at the same time. And this is how we're going to use it. So remember the 2 assumptions that we made. First assumption was that the bins are completely filled. And second assumption was that we had half of the items being in K bins and the other half of the items being in the rest of the bins. If we then take B to be all the subsets that can fit exactly, that are possibly going to fit into the first K bin. So they're of size exactly n over 2, and they're of weight exactly K times the capacity of the bins. So those are all the sets that could possibly fit into the first K bins. And once we get that set, we can compute for each X in that set, whether X actually fits into these bins, whether we can actually distribute them over the first K bins. And then we can also compute for each X whether the rest of the items can fit into the rest of the bins. And this first thing can be done in time the down closure of B, as I just told you. And the second thing can be done in time the up closure of B, which is just by mirroring the argument. So in total, we can compute both of these things. And then if for an X, it is true that it fits into K bins and the rest of the item fits into the rest of the bins, then of course we have a yes. And that's how the algorithm just runs. So it runs in time relative to the down closure plus the size of the up closure of B times n. So does this always help us? Well, no. Unfortunately not. There are cases where this is actually still a 2 to the n algorithm. So for example, if we have all the weights being 2 again, then this set B is just going to be this line of like everything of size n over 2, because everything of size n over 2 will have all weight n, because it's n over 2 items with weight 2, so they're all going to be of weight total n. So this set B is already huge, and you can imagine that the bound and the upper closure are just the whole subset lattice again, so that's not going to help us. However, in the case where we had the powers of 2 as weights, this is going to help us, because this B is now going to be of size at most 1, because we said that each weight can only be, we can only get that one time from a set H. So each B is going to be at most 1, and so also its up closure and down closure are going to be relatively small. So in general, the following holds. If this set B is smaller or equal than 1.99 to the n, then the up and the down closure together are also smaller than 1.9999 to the n. And this is not something I'm going to prove. And there's actually the assumption we heavily use that we only do things around the line n over 2 in B. Okay, so if we accept this theorem, then we actually have also a statement when this algorithm is faster, because so if this set B is smaller than 1.99 to the n, the algorithm runs also faster than 2 to the n. So we have now two statements. On one side, we have dynamic program runs faster if this alpha is smaller than 1.99 to the n over m. And on the other side, we have algorithm B running faster if B is smaller than 1.99 to the n. And so we need something to prove that either one of those two is going to be true. And this is where we came up and were able to prove the following theorem. And it says that for all delta greater than 0, there exists an epsilon greater than 0, such that if this alpha is bigger than 2 to the delta n, then B is actually going to be smaller than 2 to the n with some epsilon factor. Okay, how is this going to help us? Well, we can take delta to be 1 over m. Then either alpha of W is going to be smaller than 2 to the delta n, then that means that algorithm A is going to be faster. And if that's not the case, then we can use the theorem, and that tells us then that B is smaller than 2 to the power 1 minus epsilon n for some epsilon. And so we know that this is true, so algorithm B runs faster. But then again, how to prove this, because this is quite a hard statement and it's entirely not clear how you can prove this. And what we're going to use is additive combinatorics, and a very specific part of additive combinatorics called uniquely decodable pairs. So uniquely decodable pair is a pair of sets A and B, such that the size of A plus B is equal to the size of A times the size of B. So where A plus B is just addition, like pairwise addition for every set element in E, A and B, we're just going to sum it and put it in. And the addition is over just the integers, so we can actually get 2's in this set. Okay, where does this come from? Well, it comes from the idea that you have two people talking to a third person, and the first person has only access to a library of words A, and the second person has only access to the library of words B. And the third person then receives a message which is just a sum of these two messages from A and B. And then you might wonder, when can this person C actually know what they sent? And if this last person can always know what the first and the second person sent to him, then you know that's a uniquely decodable pair. So that's where it comes from. And just 2 examples. So the first example is where we just allow the first person to only talk around the first bit, and the second person can only talk around the second and third bit. Then of course it's uniquely decodable because we can just look what the first person said and what the second person sent. So that's an easy one. But there's also another example where, for example, we have A being 0, 1, 1, 0 and B being 1, 1, 1, 0, 0, 0, opposite 1, 1. So it's not entirely clear at first that this is indeed uniquely decodable. However, the size of A plus B is now 6 because we can make these 6 things, and the size of A is 2 and the size of B is 3. So indeed it must be uniquely decodable by that. Okay, so why am I introducing this uniquely decodable pairs? Because, well, we're looking at a uniquely decodable pair the whole time from the beginning. So before I get into why, I just want to say that I'm also going to see W as a vector instead of just a function. You can also see the weight function is just being in a product with the weight vector and the vector that I'm multiplying with. And then I define the set A as such that for all A's in A, the weights are all different. And I can define this in such a way that the size of A is then going to be equal to this alpha of W. So for each weight, I'm going to add exactly one set that has that certain weight to this A. And then I know that for every A in A, there's a different weight. And the second set that I have is going to be B, and it's just the B that we already had. We're just going to fix some S, and we just add the B's that have exactly the weight S to that set. And now my statement is that A and B are UDCP because, well, let C be the received message. I know that C was a combination of A and B, so C is equal to A and B, but I also can compute the weight of C. So let's do that. Weight of C, that's equal to the weight of A plus the weight of B. But I already knew what the weight of B was because I assumed that all the weights of B were equal to S. So because of that, I can find the weight of A. And because I said that all the weights in A are unique, I can actually find which set had exactly that weight. And I know, therefore, what the message A was. And if I know what the message A was, I can just decipher B because I subtract C minus E, and then I just get to the original message B. So just because I construct A and B in such a way that all the weights in B are equal to each other and all the weights in A are all different, I know for sure that they must be uniquely decodable pairs. Okay, some theorems about uniquely decodable pairs. One observation is that the size of A times the size of B is always at most 3 to the n, which is just an easy observation because, well, anything in A plus B must be in 0, 1, 2 to the n, because that's the only sums we can get. So there are most 3 possible things that you can get for each number. So n times that is 3 to the n. But there are better bounds. So the best known bound is actually that A times B is at most 2 to the power 1.5 n, which was proved by Tilburg in 1978. And there's another bound, which I just want to show, which is just a little bit better in case that B is really big. If B is like almost all the sets, then A is smaller than 2 to the power 1.4228 something. So this already quite looks like what we are going to prove, but we did something slightly different. So if we would just use these theorems, then if we would say that B is really big, then we conclude that A is then equal to the size of A plus B divided by B. Because we had the size of A plus B is equal to A plus B, so we just put this b on the other side. And so if we then assume that b is 2 to the n, we have this 2 to the power 1.5n from previous theorem, so we can conclude that a is at most 2 to the power 1.5n. So this is the way how you can use these theorems to get a bound on a at the size of a or b. But we need something stronger. And what we're going to use is a new set that I'm going to create, which is called k times b. So k times b is just adding k vectors from b. And the nice thing about k times b is, again, that its weights are all the same, because I just added up k things all having weight s. So the weight of anything in k times b is going to be k times s. And remember about the argument that I showed earlier, now a and k times b are also kind of UDCP. So I also know that the size of a plus k times b is equal to the size of a times the size of k times b, just by exactly the same argument that I had before. So now I can say that the size of a is smaller or equal to the size of a plus k times b divided by k times b. Okay, so now this is really hard to actually prove how large this is. And Karel spent around 12 pages to be able to give an exact bound on this. So I won't be able to explain this fully to you, but I just want to give you some sort of feeling why this might be small. So we're going to assume that b is like almost all the vectors, 0, 1 to the n. If that's the case, then we also know that k times b is also almost everything, because we could just combine everything. So this is always almost of size k plus 1 to the n. And remember that everything in a plus k times b is then going to be somewhere in the sets 0 up until k plus 1 to the power n, because that's the only values that we can get. And then we can also bound the size of that. So the size of this is at most k plus 2 to the power n, and the size of this will be then roughly equal to k plus 1 to the power n. And that we can rewrite as 1 divided by k plus 1 to the power n. And that is equal to 2 to the power delta k times n. So the nice thing about this is that we can just choose this k, we can make it larger and larger, and this delta k is actually going to be smaller and smaller. And this delta k is actually going to 0 as k goes to infinity. So this is exactly what we wanted to prove for it. So for any delta k, which is like the delta in our theorem, we can prove that b then must be like not completely. Okay, so I'm going to leave the proof at that. If you have questions about it, I recommend maybe asking Karel as well, because he's, I think, the expert at this moment about it. But I do want to show you something else, and that is how we got rid of the assumptions. And I'm not going to into deep, but just to show you that it's not easy to get rid of these assumptions. So the algorithm goes as follows at this moment. We had either alpha is going to be small, and then we could apply algorithm A, or we had these two assumptions. So, okay, so if alpha is greater, then we could conclude that B is smaller. And if we then assume that we have a balanced solution and there are a lot of 5 bins, then we can use algorithm B as before. So that's still everything what we showed. But we still have these two assumptions, like what happens if we don't have a balanced solution. And if we don't have a balanced solution, we can actually modify algorithm B in such a way that we're just going to guess the sets. And because it's unbalanced, we have a high probability that we're going to guess the right sets. And in such a way, we can still use the same algorithms actually. However, if it's balanced, but we have a lot of bins that have a lot of slack, like there's a lot of space left, and then we need to do something a lot smarter. And that's where we kind of combine algorithm A and B at the same time. So we're kind of combining a dynamic program with a fast set and Möbius transformations. And we do that by actually not computing with the actual weight functions, but we're computing everything with weight functions W theta. And this theta then depends on some weird way on the weight function itself. But we're going to, this weight function is just going to prune all the weights to just the first theta bits. And by doing that, we can make sure that actually the number of different weights, so the alpha of W theta, is going to be small again, which allows us then to use the dynamic program in kind of like a new way. I think I'll leave it at that. I think that's complicated enough. So just describing this last algorithm also just takes 1.5 pages. But it's really interesting that we were able to get rid of these assumptions in these ways. So that's already my conclusion. The main result is that we did something faster than 2 to the n, like 1.99 to the n, where this epsilon then every time depends on the number of bins. And then the key idea was that there's a trade-off between these parameters, alpha of W and the set B. And then either algorithm A is going to be small or fast, or algorithm B is going to be fast. And of course, future research, it would be really cool to show for bin packing in general, for a non-constant number of bins, that it's faster than 2 to the n. However, a lot of our ideas really work on this assumption that m is constant. So you really need new ideas and new insights to come to a faster algorithm. So I'm not sure whether it exists, but I think it might be a hint that it might exist. I think that's, I'll leave it at that. So thank you all for your attention.
Thanks a lot for a great talk. So maybe we on 3, 2, 1 we can unmute ourselves and clap. So 3, 2, 1. Good. You can mute yourself unless you have a question. Are there any questions to Céline? Please don't be shy. It seems that we don't have any questions. So yeah, thanks.
Actually, I do have a question.
Good. Yeah.
I have a question. So these results about like this uniquely decoded pairs, they were also pivotal to this series of papers. I don't remember exactly about like subset sum. There was like a stacks paper and some other papers about stacks. Does this improvement, like this idea of like not looking at A plus B, but A plus K times B, does it also help with the subset sum things that were there a few years back?
So it doesn't really help it out there.
Okay.
That's unfortunate, but yeah, no, it doesn't work out. It doesn't help it much further.
Okay, thanks.
Yeah, I think I also seen this this kind of tricks. There was this stock paper of Jesper and others for subset sum, and this the trade-off between the number of different pairs and the number of buckets, the number of different buckets and the number of the multiplicities was also used there. So yeah.
Yeah, so you can see why we got Jesper on this project and where we got our ideas to get this result.
Yeah. If somebody is interested, actually 2 years ago, we gave a problem on this to the Math Olympiad for high school students on the first round. So there's a nice problem about this there. Yeah, so I recommend it. Good. Any more questions?
I have a question. I'm interested, what are the values of this 2 minus epsilon for small values of m? Like m equal 2, 3, 4, 5. Is it anything significantly below 2 for small values of m?
So we didn't optimize our analysis for it because at first we tried, but then we just made it harder. And in the end, the epsilon values were small. Let's say I don't remember exactly, but I don't think they're bigger than 0.001 or something. So yeah, it's faster than 2 to the n, but yeah. I don't want to see the epsilon for example, 100 machines. I think that's extremely small.
And these previous results for 2 bins, what was the time complexity exactly?
So for 2 bins, it's just a subset sum. It can be done in 2 to the power n over 2. So that's square root 2 of n. And for 3 bins, that we remember, I think the algorithm ran in m to the power n over 2. So that's square root of 3 to the n. And that's also why for 4 bins, it's exactly equal to 2 to the n. So for 3 bins there, the sort and search algorithm is definitely faster. And then for 4 bins and on, in theory, we can do better.
I see. Yeah. Okay, thank you.
Sure.
But it makes sense to, for instance, look at the special case of 4 bins, 5 bins, and try to get something reasonable.
Yeah, definitely. Yeah.
Okay, any more questions? If not, then thanks, Céline, again. You are actually our first international speaker in this seminar.